Pre-calculus on Earth. Boom, 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 boom. Back with another instructional video. It's Mr. Berto. Hope everybody's safe and healthy out there. We're continuing related rates. It's Friday. That's why I'm in such a good mood. I hope you tried your homework. Related rate problems aren't really too terrible. They're much more mathematical than those optimization problems we did last topic. So hopefully you're enjoying them, okay? A couple new things showed up. Homework, by the way, I'd like to think that number 1 was actually really easy. Classic type of problem right there with a sphere. Number 9, also pretty classic, very similar to a problem that we did, I think, on the second day of related rates. What are we up to? I think maybe the 4th day right here. Just try to remember, right here, they tell you the rate at which the rope is being hauled in. That means this distance is getting smaller. Hence, his rate of change needs to be negative. Rate of change needs to be negative. That's what a lot of people flub up with these problems. We spoke about that. Number 2 is also pretty classic. Sorry, stuff is out of order here. Number 5 was cool because they wanted to know the rate of increase in the area of a circle. So they wanted dA over dt. They told you what dr over dt was, but they told you dA over dt at the instant when the circumference is equal to 20 pi. So after you set up your area function, you differentiate both sides. You're like, what the heck is r at this particular instant when the circumference is 20 pi? Well, you could easily just actually solve for r using your circumference formula. When circumference is 20 pi, what is r equal to? So it's not really that bad. If you're really good, by the way, you realize 2 pi r is circumference. You could just taken the whole 2 pi r, replaced it with 20 pi right there. And I showed that down here. It's impressive if you actually realize something like that, okay? It's not always going to work. We had that one that we did yesterday where you had to not just use information they gave you to figure out what r was at a certain instant. You also had to use other information. They gave you, like dv over dt. You had to figure out what dr over dt was. So, pretty popular types of problems there. Let's jump into it because there was another thing that we dealt with on, the last lesson. I think it was 2 cars starting at the same place and at the same time. And they actually wanted to know how quickly the distance between them was changing. What's the rate of change of the distance between them, like 30 minutes later or a half hour later? So they didn't actually indicate that specific instant of time by giving you a measurement of a distance. They gave you a measurement of time, and that's going to happen here. Great little problem from a textbook. This textbook has nice little, sentences, titles for each problem, like hauling in a dinghy. What's a dinghy? It's a small boat used to get to your big boat out in the harbor, okay? It's my boat. That was a homework problem. Let's look at number 8, a balloon and a bicycle. Bicycle. All right, so a balloon is rising vertically above a level, straight road at a constant rate of 1 foot per second. Smell a rate. Just when the balloon is 65 feet above the ground, a bicycle driven by Connor Crowley passes under it going 17 feet per second. I smell another rate. How fast? They want a rate. Is the distance between the bicycle and the balloon changing 3 seconds later? So it's not telling you an actual measurement. It's telling you at a time. Then it suddenly lapses into this weird font. How fast is the area of the triangle changing then? Reminds me of like some SpongeBob memes. Anyway, so it's actually just really a part A and a part B. So let's look at this again. A lot of words. A balloon is rising vertically above a level straight road at a constant rate of 1 foot per second. That's the rate at which this distance is changing. They give you a nice little diagram right here. They call this y of t. There's other ways to do these problems. This is a parametric equation type of setup where we're going to figure out what the height is in terms of t. We don't really do that way in this class. We just say if something's changing, we label it with a variable. And they actually tell you the rate at which this is changing, dy over dt. They told you it was 1 foot per second. And then just when the balloon is 65 feet above the ground, so when it's been rising for 65 seconds, the bicycle passes underneath it. Remember, driven by Connor Crowley. So here, let's use my amazing skills. There's Connor right there. His hair is like blowing in the wind, okay, because he's on the bike. The bicycle passes under it going 17 feet per second. We want to know a lot of information 3 seconds later. After 3 seconds elapse, then Connor's going to be all the way over here. So let's draw that bicycle again. Connor Crowley on the roll, getting stuff done, man. He's probably driving somewhere to call me a nerd. It's not very nice, Connor. Anyway, so this right here originally is the distance between Connor and the balloon. But you can see as you move to the right, This represents the distance, this line segment between Connor and the balloon. So right here, the distance between the point directly below the balloon and where Connor is, that's going to be variable as well. They call it x, and they define a function in terms of t, x of t, to tell you the distance. You can just call it x if you want to. Remember, if this distance is getting bigger and this distance is getting bigger, at the same time, this distance is getting bigger. Let's just call it s, this distance right here. You know, they actually told you the rate at which this distance is getting bigger. That's how quickly Connor's driving his bike, right? dx over dt, 17 feet per second. So the rates that they gave us in part A, they want to know how fast is the distance between the balloon and the bicycle increasing 3 seconds later. So part A, hopefully a part A. What do they want? Well, they want the how fast, which is the rate of change, usually, the distance between the bicycle and the balloon increasing 3 seconds later. That's the rate at which s is changing with respect to time. ds over dt, ds over dt. Okay, and we want that. And as far as the when, well, 3 seconds later. You could say when t is equal to 3 seconds or something like that. And the idea is that we'll use that information to figure out what values are at that instantaneous time t. But before we do that, we need a formula that relates the variables. It needs an s in it. There could be an x, there could be a y. Right triangle, you know, try to go with the Pythagorean theorem. There's another formula, the area formula, which we haven't talked about yet, but we're going to talk about that in part B. But right here, x squared plus y squared equals s squared. And that is in flux, just like the diagram is in flux. It works for any time t, anything that's variable labeled with a variable. Same thing with the actual formula. Differentiating, even though there are 3 variables, is easy. You know, 2 variables on one side, I don't care because of the addition. So differentiate implicitly with respect to t. 2x dx over dt plus 2y dy over dt equal to 2s ds over dt. Believe it or not, the numbers do get a little wonky here, so this is a calc assist problem. But we're going to try to avoid it for as long as possible, okay? I mean, even if you are using the calculator, I divide by 2 on both sides, okay, because it just makes things a lot easier. Remember, ds over dt is what I want, so the x has to go, the dx over dt has to go, that's 17, I know what it is, plus the y's got to go, the dy over dt's got to go, that's 1, I know what it is, s has got to go as well, and then we'll leave the ds over dt. So we need x, y, and s right here. And, you know, I wish we were in class together because this is the point where I'd ask if somebody could figure out what either x is equal to or y at this particular time, or s. I might remember, you know, earlier in the year, what was it, like October or something? You know, people were considering a raid on a certain government installation. That actually becomes a real part of this because at this instantaneous moment, x is actually equal to 51. You know, 51, area 51. Where'd that come from? Well, 3 seconds later, now the diagram is stopped. And how do I know x is equal to 51 3 seconds later? Well, Connor's riding his bike at 17 feet per second, right? So if you actually take that 17 and multiply it by 3 seconds, you get 30 plus 21, which is really 51. So I know x is equal to 51 at that specific instant of time. And then a lot of people are like, oh, I know what y is equal to. That's easy. dy over dt is 1 foot per second, 3 seconds later. So y is equal to 3. It's actually incorrect, okay? Because you might remember when Connor passed underneath the balloon, it was already 65 feet above the ground. So it was already 65 feet above. Now 3 seconds elapsed, so it rises 3 more feet. So that's why it's actually 68 feet right there. And this is where you'd use the calculator to figure out what s is equal to. 51 squared plus 68 squared equal to s squared. Unless your last name is Chestnut or Harrington, tough to do that without a calculator. Or is it? Because there are things that those of us who can't calculate ridiculous mental math things, we're not robots, all of us, in their head need to do. Here's what Mr. Berto needs to do for this. Try to think about it. The most famous Pythagorean triple is a 3, 4, 5. 3, 4, 5 Pythagorean triple. If you kind of think about this 3 right here, 17 times 3, if you actually do 17 times 4, that gives you 68. That's 40 plus 28, which is 68. So this is actually a 3, 4, 5 Pythagorean triple dilated by 17. Who thinks about these crazy things? Only crazy math people like me, just to avoid doing crazy mental math or to avoid using a calculator. So this is doable. What is it? 50 plus 35 is 85. So it's just the 51, 68, 85 Pythagorean triple. Nobody knows about that. Okay, so once again, if you want to say y is 68 and then use the calculator to get that this is 85, don't worry about that. That would be fine. And then you can get what ds over dt is equal to. And I'll use the calculator for that, even though this calculation is not so ridiculous, but it's just not stuff that you see anymore because people end up wasting too much time. This is from the problem we did the other day. Notice the way it's set up. Just like what I'm going to do for this, okay? I could even hit second enter to get that back and now manipulate. Ain't it great? So I want 51 times 17 plus 68 times 1. Okay, and down here, divided by 85, and I divide by 85 on both sides. The year Marty McFly traveled back in time. Okay, and I actually get 11 right there. So I know that ds over dt is what really loud amplifiers go up to. This one goes up to 11. Who gets that, what I just said? I know Stavros gets it. Does anybody else get it? So 11 units. I need units. And think about S. It's a linear measurement. This distance right here. So it's going to be a linear distance, which is going to be feet per your unit of time, which is seconds right there. Remember, if it's an area, put square feet per second. If it's a volume, just cubic feet per second. So part A is really not too terrible. The only thing that's different is this right here, and it's similar to something we did yesterday. If you look at part B, now they want to know how fast is the area of the triangle changing then? Well, that's dA over dt, or da over dit. And that's the same time, right? 3 seconds later, which is useful because I have a bunch of information about what distances are equal to 3 seconds later. The problem is dA over dt, you need a formula that represents area. How do we get area of a triangle? 1/2 base times height. And the great thing about a right triangle is you could always say the base and the height are the legs. You don't need to. You could say the base is the hypotenuse. And then you get the height, this distance here. But then it gets really annoying. I mean, it's doable, but it really makes problems a lot more difficult. Right triangles, the leg and the two legs, they'll always form a right angle. So it doesn't matter how the triangle is oriented. You could always do 1/2 leg times leg. So I'm going to do 1/2 x times y. And the problem with that is now you're multivariable on the right. But Mr. Beto, we were multivariable on the left over here. Yeah, but the variables were connected by, were connected by addition. This right here connected by multiplication. Product rule, okay? And people are like, product rule? How can we use a product rule here? Well, remember, don't you dare just take these two derivatives and multiplying. Don't you dare do that. Take two derivatives and multiply. Don't be a slacker. Really, when you do the product rule, second times the derivative of the first, plus the first times the derivative of the second, people are like, but Mr. Beto, when I do the derivative of the second, a dy over dt is going to show up. And that's true. A dy over dt will show up when you do the derivative of the second. I don't care. I know what dy over dt is. But Mr. Beto, when I do the derivative of the first, a dx over dt is going to show up. Yeah, a dx over dt will show up, but I don't care. I ain't even mad because I know what dx over dt is. So product rule is not a big deal if you actually know the values that you need to know. Like if you just had dx over dt, you just had dy over dt, then you might want to make this univariable. But it's really difficult to do here because all the sides are variable, so you'd end up introducing an s anyway. So it's not really viable for this problem. It's more viable for the types of problems when, one of the sides is constant. But regardless, product rule, second, right? The second function we know is y times the derivative of the first. And what's the derivative of 1/2 x with respect to t? Well, the derivative of 1/2 x is 1/2, but don't forget that dx over dt next to it got to indicate respect to t. T, I'm gonna give you respect on this, the day your daughter's wedding. Plus the first function, first, 1/2 x, times my personal favorite, derivative of the second. And geez, I wonder what the derivative of y with respect to t is. It's dy over dt. Come on, folks, wake up. And dA over dt, that's what I want. Bo-no-no, bo-no-no-no-no-no. That's what I want. If you know that old tune, it's like a 50s tune or something. Anyway, let's replace, okay? I know what y is equal to. Is equal to what? 68? 60's not hungry because he ate. 1/2 times dx over dt, which we know is equal to 17. The age of some people listening to this video. Plus 1/2 times x, so x is 51. times dy over dt, which was 1. So if you actually leave that out, you would be fine. And here's where the calculator comes into play. I think you really need it. You could do this without a calculator here, but we have it, so why not flaunt it? 68 times a half is 34, so 34 times 17. Plus 1/2 times 51, so 0.5 times 51. So I get 603.5, the number of dates I had this weekend. I have this weekend coming up. One of them is not really going to work out that well. I'm going to have to leave in the middle of it. Anyway, so dA over dt, come on, that was funny, is 603.5. And I could hear you screaming right now. I'm about to circle that and walk away. You should be like, no, Berto, no. And you should be screaming something out. What are you screaming? That's right. Units. I want units. Okay, and as far as the units are concerned, it's the rate at which an area is changing with respect to time. People are like, yeah, feet per second. Yeah, because when you measure area, you really use feet, right? When you go to Home Depot, you're like, I need 2 feet of carpet. They're going to be like, wait, feet or square feet? Okay, that's the measurement of area. So that's square feet per second. So cool problem right there. Balloon and bicycle. Bicycle. Got to be a Queen fan to get that one. Is that Queen? I think it is. Anyway, so a cool type of problem there, and really it's just related rates day 4. One more day on this, that's Monday. You'll have a take-home, assignment. I'll give you Tuesday to work on that. Then we're actually done with chapter 3, applications of the derivative. We're going to move into chapter 4, integration, which is anti-differentiation. So if you hate the derivative, you're like, I hate the derivative, I hate differentiating, I'm anti-differentiation. That means you're for the integral. Integration, anti-differentiation. Much more difficult than differentiation, but much cooler. So we'll be talking about that. After that, there's only one more little sub-chapter, and then we're done with the curriculum for the year. Am I going to see you guys again? I don't know. I really hope so. I miss you, some more than others, okay? But I definitely miss all of you in class. I don't know if I'm going to see you before the end of the year, but I know I'll see you next year in either AP Calculus AB or AP Calculus BC. For those of y'all willing to step up to the plate, and if you're not doing your work, don't step up to the plate. Right now, call guidance and be like, take me out of that class, because you're not going to be prepared. This is Calculus Light. We need to go through this. So next year, we could really rock and roll, especially in BC, where I'm planning on cutting all the AB topics in half, doing them that much quicker. So imagine every topic we had, we only did it in half the number of days. So this topic is 5 days. We only do it in like 2.5 days. Some people are like, good, because this is really boring. I'm really good at it. Other people are like, oh my God, that's way too quick. So think about that with BC. It's not BC that people can't handle the calculus always. Some of it's pretty rough, but it's more the pacing thing. So anyway, something to think about. Make sure you do your homework problems tonight. One final lesson Monday, assessment Tuesday. And once again, I hope you guys are all healthy and safe. That's the most important thing. I want to make sure that you guys are all right. If you got questions, text me, through Remind or email me. We could do screenshots. I've been helping people out that way. Don't be afraid. Ask me the questions, Bridgekeeper. I am not afraid. Stavros gets that one too. Anyway, so here's another pre-calculus honors instructional video. It's over, but there'll be another one really soon on Monday. In fact, I'm going to record it right after this one. So I'm psyched. Berto signing out. See you later, y'all. I see you later, y'all. I see you later, y'all.